today. Dr. Müller, thank you for joining us. Thank you for ready to deliver this lecture on this very very interesting maybe topic which in high demand, because we are facing right now many challenges in agriculture right now, especially because of climate changes. So everybody will take everything good and will take many knowledges and will apply it in their research activities, and wish you fruitful lecture and cooperation. Thank you, Dr. Müller.
Thank you very much. Thank you very much. So, Mr. Müller, I hope that you can hear us. You are also in English channel and everything works well. So hopefully we could start. We can see your presentation, and I have already mentioned that our participants could write their questions, technical ones, should they have some, in our chat. So please moderate your lecture. Podium is yours.
Thank you very much. Thank you for inviting me and for the warm introduction. I am very happy that I can talk about this, as you already said, very important topic, as I think also for Ukrainian agriculture, but also for agriculture in any part of the world. So in case I speak too fast or too loud or too soft, then just let me know and I will adapt accordingly. So in this seminar, I hope that I can raise some more research interest in this topic and that you will leave with some interesting and new insights. Just a few words about me. I'm an agricultural economist by training and work at the Leibniz Institute of Agricultural Development and Transition Economies. And I also serve as a lecturer in geography at Humboldt-Universität zu Berlin. In my research lab at IAMO, we worked on the connections between climate change and agriculture for quite some time now. And we specifically do research on options and challenges of emissions reductions in the land use sector, on the mitigation of emissions, and on adaptation pathways of agriculture to climate change. Our geographic focus is on the former Soviet Union countries as well as China, and we also do quite a lot of research in Ukraine, and we intend to do more research in and about Ukraine, so every input from your side is also very warmly welcome. So for the interactions in this lecture, I tried to use a Slido where I have set up some surveys, polls, and some question and answer tools. So if you have a smartphone ready, then please scan the QR code on this slide, or on your laptop, go to slido.com and then enter in the browser, one second, CC-UKR, climate change Ukraine, as the code, and which will bring you to the Slido page of this lecture. So via Slido, I would be very pleased if you can just post your questions and opinions, and then we have some sessions dedicated to discussing these questions and opinions. You can post questions anytime via Slido, and then we will try to discuss these at the end of each block to the extent that time will permit. If you note down the question number to your slide, we can also revisit some of the slides so we can have a more substantiated discussion. Okay, and so to start off with this, I want to start with Slido. I think I have to activate. I hope everything works as planned. So there should be a poll now open for you on Slido where you can enter the questions. I hope this works. And we have posted several questions. It should come here on the fly. Not sure if anybody's already entering. It has worked before. Is the poll activated for all of you? Can you see it?
Yes, we can.
Yes.
Okay, so in theory, if you answer these questions, yes, it's working. The students are the quickest. Maybe take some time to travel from Ukraine to my screen. So here I just want to know a little bit more about who is participating today, so then that I can try to target a little bit how I talk and what I talk about. I may skip some slides that may not be relevant to the majority of the participants here. So I just wait a little bit until some of you have filled out these slides, these questions. And I will also distribute these surveys to you after the call. I can download these afterwards. Now, come on, there are a few more than 8 people in the room here. So I hope it's working for most people.
Probably we should add that for sending your response, you should choose send in the end. Not only choose the answer, but also choose the button send, and then your answers will be verified for this questionnaire.
Okay, thank you. Thank you. Yeah. At the bottom, there's the send button. So if you just answer these questions. Okay, so I think I continue here in order not to lose too much time. I will distribute the full responses to you, as I said, after the slide. So most of you are younger than 30 years, as most of you, at least those who have filled out the survey, are students. A few more responses come in. And most of you join because of interest in this topic, and not because they have to join, which is, I think, good news for me. And most of you already have quite substantial knowledge about the causes of climate change. And some of you already do a little bit of research about climate change, but some of you don't. So I hope that I can raise your interest in this topic and move a few more to the bottom part here. Okay, so much to the warm up. Now for today, I have prepared 5 main blocks that I will spend the remaining about 70 to 80 minutes on. And after each block, I allocated a question and answer session. So again, if you have a question to any of the slides, please enter these questions to Slido, and then we can revisit them on the screen, and I will try to answer as many as I can. And I can also spend some time after the lecture to try to answer some of the questions that could not be answered for the sake of time. So what I will do today, I will briefly introduce you to the scientific basis of climate change. I will talk a little bit more in detail about extreme weather events and their importance for agriculture. I will talk about the impact of climate change on agriculture in generally and globally, and then focus on climate change and Ukrainian agriculture, and then end with some adaptation option and future research priorities. So very shortly, climate change in 16 words. We know now that climate change is real. It is not some fake news. that have been introduced by some socialist governments. It is very dangerous also for agricultural production, as I will show along this seminar. It is very clear that humans cause it, and all experts basically agree on the fact that humans are more or less the only cause for the climatic change that we observe. And we can still, we still have some time to reduce the impacts of climatic change on humanity and on agriculture in particular, but time is running out very quickly. Okay, so how do we know that climate change is actually happening? Though we know this, for example, from the Dome Concordia station in Antarctica that sits on more than 3 kilometers thick ice, and that is away more than 1,000 kilometers from the next animals, living animals. On this Dome Concordia station, scientists have scored and had a drilling project between 1996 and 2005, where they drilled an 800,000-year-old ice core out of the ice with a 10-centimeter wide cylinder that goes down almost 3,000 meters, 3 kilometers, almost down to the bedrock. Yeah. Okay, so and each of in these, if they slice this ice core, they see they have these small ice slices where each of these little air bubbles inside is like a little time capsule that records the ancient atmosphere's contents. And using this, this 800,000-year-old ice core, we can record temperature and atmospheric carbon dioxide over these, over the age of this ice core. And from this, we see whenever in the past the Earth went to an ice age and when temperatures fell, concurrently the concentration of greenhouse gases in the atmosphere also declined. When the climate warmed back up again, also CO2 in the top row here also increased in parallel. We can also see that ice ages occurred in cycles of roughly every 100,000 years that are linked to the slight shifts in the ellipse of the Earth around the sun. Now here's another representation of this ice core measures for about the 800,000 years into the past. We can see very stable CO2 concentrations between about 180 and 300 parts per million that went right through the Holocene, where we have been in until recently, where CO2 concentrations have been on average about 280 parts per million. However, something happened in the recent 50 years when CO2 concentration shot up in the atmosphere, shot up substantially. And this is what scientists now call the Anthropocene. We are in an age that is shaped by humanity, not by natural cycles any longer. So if we look at these past 50 years, here's a graph of the accumulation of carbon dioxide in the Earth's atmosphere based on continuous real-world measurement. You probably have seen this graph already. It has been named for the scientist Charles David Keeling, who started his monitoring program in 1958 until his death in 2005. He monitored CO2 concentration at Mauna Loa Mountain on Hawaii, which is an ideal location because it's very remote from continents. It lacks vegetation and therefore has a clear measurement. As of April 3rd, and the last number that I found when preparing the seminar, CO2 concentrations have been at 421 parts per million. So this is more than a 50% increase compared to the Holocene. In fact, humans emitted much more than these additional CO2 concentrations, but about 40% of the emissions that humanity emits are absorbed by oceans and vegetation. But in any case, humanity, the CO2 levels and that we are emitting today are higher than at any time for the last 3 million years. And some scientists claim that CO2 concentrations are higher than for the last 15 million years on Earth. What is happening here? Okay. So, this is of concern because of the so-called greenhouse gas effect that was already discovered a long time ago by Joseph Fourier with his book on the theory of heat from 1822. It was worked out further later on, and what these scientists basically said 120 to almost 200 years ago was using basic principles of physical chemistry. They said that the amount of atmospheric carbon dioxide will increase the Earth's surface temperature through the so-called greenhouse gas effect, just as with the greenhouse gas that we use for plants. So they concluded that human-caused CO2 emissions, mainly from fossil fuel burning and other combustion processes, are large enough to cause global warming. And because greenhouse CO2 is an atmospheric gas that absorbs outgoing energy. There are other greenhouse gases such as water vapor, methane, nitrous oxide, and ozone that also cause that also absorb outgoing energy and act as a greenhouse, basically. And adding and removing these absorbers changes the radiative capacity of the Earth. So if we would strip away the atmosphere of the planet, then the planet's temperature would be about -18 degrees, and there would be basically no life on Earth. So the atmosphere is absolutely crucial for any life on our planet. So the real world is, of course, very complex because of many feedback mechanisms. If we would model the climate or climate change on the moon, this would be very simple because the moon has no atmosphere, the moon has no oceans, no ice caps, no seasons, and no complicated fauna and flora that gets in the way of simple radiative physics. So without atmosphere, the sun just emits radiation, the Earth absorbs some of the incoming radiation and reflects back the rest of it. And temperature would be very easily calculable based on the albedo or the reflectivity. So the first climate model is very old. Already in 1967, some scientists have used physics and came to the conclusion that in their words, according to our estimate, a doubling of CO2 content in the atmosphere raises the temperature of the atmosphere by about 2 degrees. And as I have just shown you with empirical data, as of now, CO2 has increased by about 50%, and we reached a temperature increase of about 1%. So it seems this model from 1967 have been actually very accurate. Also, other people already know this before pretty exactly. Here is from the hydrocarbon oil giant ExxonMobil. Their projections from 1982 almost exactly match what we have seen today, about 420 parts per million CO2 concentration in the atmosphere in 2021, and a temperature increase of just above 1 degree Celsius on average. So ExxonMobil have this memo, which of course they didn't publish because it would ruin their business, but they knew pretty exactly about the so-called CO2 greenhouse effect, and they could model the effect of rising CO2 concentration on surface temperatures very exactly already 40 years ago. Okay. So what are the most important greenhouse gases? Very briefly, you know them all. There's CO2, methane, CH4, nitrous oxide, N2O, and some some trace gases. I want to concentrate on the upper three. So CO2 is, with its global contribution, by far the most important emission, mainly through the burning of fossil fuels. It has a lifetime of 120 years, and that is very important. And the global warming calculated to compare the greenhouse gases for over 100 years. A warming potential of 1 by definition. That is what we call then here the CO2 equivalence. Methane, which is responsible for 16% of the global emissions, has only a lifetime in the atmosphere of about 12 years. So its global warming potential of over 100 years is a lot higher, because it only persists for about 114 years in the atmosphere. However, relatively speaking, the impact of methane in the short run is extremely important. So, for example, if you calculate the impact of methane over a period of 20 years instead of over 100 years, then its global warming potential rises to 72. And that means that if we want a fast reduction in emissions, methane is really one greenhouse gas that we need to focus on because of its high warming potentials over short time periods. This is just to complete what I said in the introduction. This is the contribution of individual sources. Here are two natural sources, solar radiation and volcanic eruptions. They contribute very little to climate forcings. It's really overwhelmingly human activities that contribute to the increase in radiative forcing through the emissions of greenhouse gases. So humans are responsible for all experienced global warming, and natural variability contributed very, very little to climatic trends over the last decades. And this leads to these warming stripes here that you have probably seen before, where each color stripe represents the temperature of a single year, ordered from the earliest available data on each location to the present. So all superfluous information is removed to really emphasize the changes in temperature that we have seen in a simple way. So this is the global average temperature change, and you can see how the color becomes increasingly dark red towards recent years. This is the same data as a similar representation using same data. Again, the global mean temperatures here. If you would look at this over the long run, that you can see that the global mean temperatures are higher now than ever since Homo sapiens arrived on Earth about 300,000 years ago. The warming rate that we observe over the last 100 years, 1 degree over about 100 years, is 10 times faster than the warming rate after the last ice age ended more than 12,000 years ago, where temperatures increased by about 1 degree in 1,000 years. By the way, at the end of the last ice age, the sea level was about 120 meters higher because of all the melted ice than it is today. So in the long run, sea level rise will erase a lot of the surface that we are currently using. So these numbers are annual global mean temperatures for all for all surface of the Earth, including land and oceans. If we summarize the global mean temperature for the land mass only, then we already have a temperature increase of 1.5 degrees with the same baseline, which is much faster than the increase over oceans, which is on average only 0.6 degrees. This is because more continental land masses warm faster, and the more continental the climate is, then land masses warm even faster than the average land mass. And this is also important for Ukraine, and even more important, so for example, for Central Asia, where we do a lot of our research, because these regions are characterized by a fairly continental climate, and as a result, the land masses warm faster than the global average. Okay, here are these curves that you have seen before, again, with a different representation. You can see the historic temperature change with a 1 standard deviation as the shading until 2005 in this case. So this is what we have seen so far. And what could happen in the next about 80 years is really much, much more. And considering to what will happen, what we have seen so far may really be peanuts. So here are the global mean temperature projections and their uncertainties for 4 major scenarios of the IPCC from a number of global climate models. So this is, of course, a major worry because already now for many of exposed and vulnerable communities on Earth, even the gradual changes in rising temperatures that we have experienced so far already had very extreme impacts, and with the extent of further warming that is expected, we will see much more of these extreme impacts of extreme weather events and of extreme climate events. So really, the future may really be much worse than what we have seen so far. Here is what the global community achieved to agree, is the Paris Agreement that intends to limit average warming to about 1.5 degrees compared to pre-industrial levels. So this will really be very difficult to achieve given the current emissions trajectories. And to end here, I want to show you the so-called carbon budget bucket that shows, I hope it's working. What's that? Here we go. Okay, so these are the cumulative CO2 emissions from 1850 to 2018. And it shows the emissions that are remaining, that we have still a 50% probability of reaching this Paris Agreement, the goals that have been put forward in the Paris Agreement. This means only 9% is left. Can I run this again? This means that only 9% of emissions are left in order to fill this bucket for the Paris Agreement. In fact, Germany's highest court has decided on a landmark climate case this April 2021, about 2 weeks ago, that Germany's climate protection legislation are unconstitutional because it places too much of a burden for reducing greenhouse gas emissions on the younger generations. In other words, the German highest court said that the carbon bucket is already too full and the government needs to act much more quickly than it had acted so far. Okay. So, and with this, we are at our question session. So now these questions should actually appear here on my slide. 1 second, please. I'm trying to fix that.
Right now, I can see that we have one question in our chat.
Okay.
It's from Mr. Wojtenko. In early Permian, the carbon dioxide content was 3%. The biosphere felt great. How can this fact be explained?
Okay, so can you please repeat the question?
Yes, of course. So in early Permian, the carbon dioxide content was 3%. The biosphere felt great. Now, how can this fact be explained?
Okay, so this is a long time ago. I don't know about the climate in the early Permian, but what we know is that so the early Permian has been much before this period. What we know from the ice core measurements is that even at these above 300 parts per million, we observe for reasons that are purely physics, a very rapid temperature increase that is much faster than it has been ever before. And in this Permian, there were no humans yet, so I really think that we have to worry about these increases here, because they lead to a temperature increase that have never been observed before in the last 3 million years.
Okay, thank you. Hopefully that would be enough for a response. I see another one question from Mr. Silchenko. Do you think the X Prize competition will help in the fight against global warming? What do you think about the possibility of removing carbon dioxide from the Earth's atmosphere?
Okay, the first part I didn't understand, sorry.
Do you think the X Prize competition will help in the fight against global warming? Probably should be explained what is X Prize?
Yeah, that would be good. I don't know.
So, Mr. Silchenko, could you please explain us what do you mean? And maybe then the second part of the question, do you think, or what do you think about the possibility of removing carbon dioxide from the Earth's atmosphere?
Okay, so there are plenty of opportunities to remove carbon dioxide from the atmosphere, but they are summarized actually in two strategies. One is to absorb carbon dioxide in vegetation, for example, through growing trees, forests. And the other is through absorbing or sequestering carbon dioxide in the soil as soil organic carbon. Both will be crucial pathways to reduce the CO2 content in the atmosphere, and both are part of all climate mitigation strategies and of the scenarios that are put forward by the IPCC, vegetation and soil. There are many studies about how much can be saved. So of course, land on Earth is scarce in many places. So we cannot just reforest everything, because we need to produce food. We need to produce more food even in the future because of rising population and rising living standards. So there is a lot of land competition about this area. Another important strategy is to sequester carbon in soil, for example, through reducing tillage operations, through working in carbon or coal into the soil, and other strategies that increase soil organic matter content. Yeah.
Okay, thank you. We have achieved this answer. I suppose it's explanation about what does it mean X Prize. That should be a competition of Elon Musk. Have you heard something about this?
Okay,
I should admit that I am not accurate. Sorry.
I heard of it, but I don't know exactly what it is about. It is probably a grand strategy by Elon Musk, who has many crazy ideas, and I hope that it will bring something good. But about the specifics of this this competition, I don't know. I cannot say much.
Okay, thank you. Maybe next time we will come back to this question, or maybe Mr. Silchenko, you can share with us this information if you have something more or your opinion about this. Okay, I see we have one small comment from Mr. Wojtenko to the or for the previous question that was about 300 million years ago. We use coal and oil due to this organic. I suppose we are talking about this early Permian, when the carbon dioxide content was about 3%. Okay, thank you very much.
Можете запитати, як справи?
So I suppose that we continue our discussion. I see another one question from Ms. Salnikova. What directions of research global warming are the most perspective now?
Well, there are a lot of research avenues that we could pursue. Generally, one part of the research directions is to mitigate emissions. So for us, for example, to mitigate emissions in the land use sector. This means produce fewer emissions per unit of food output, for example, through more efficient use of fertilizer resources, through less livestock production, through securing and sequestering more carbon in vegetation or soil. The other main direction that we will also talk about later today is to adapt to the ongoing consequences of climate change and to prepare better for the consequences of future climate change. And there's also a lot of research to do in this avenue, and I will mention some ideas that are more related to Ukrainian agriculture later on.
Okay, thank you. And maybe the last question for this question part from, I don't know, Miss or Mr. Bogdanets. What nearest consequences of climate change do we expect for agriculture in Europe?
Yeah, thank you also for this question. I will talk about some of these consequences with a focus on agriculture. There are a lot of consequences. It really depends on the sector that you look at. So for humans in general, one major impact is heat and extreme heat, particularly in summer. I will have an example later on. For agriculture, I think the main impacts will be the rising volatility and increasing frequency of extreme weather events that are difficult to prepare for. And I will also discuss about these in more detail in a few minutes.
Okay, thank you very much. Hope it was enough for now. So dear colleagues, you can use, as it was mentioned, Slido for posting your questions, or you can write it in our chat. We will have another one or two, I suppose, possibility to answer your questions. So please think about it and write it to us. Thank you.
Yes, in Slido, you can also post questions anonymously. You don't have to enter your name. People can also upvote your questions and give you a thumbs up. I have to do that online, so I can give my, so it is useful, but I don't want to force you to use it. Okay, so let's continue. And this is what I have already mentioned. I think it's the major impact for humans, but also for agriculture and for nature in particular. So this is the second block of this seminar. So with climate change, here we have a very low emission scenario, 1.5 degree world, which is very difficult to reach only with extreme reductions of future emissions. And here is the emission scenario with high emissions. This is the current emissions pathway that will arrive at a very high radiate forcing. So the result of this high emissions pathway will be a much hotter and more humid climate. At the equator, which you see in both projections here and here. At the equator, where conditions are already hot and humid, the change will probably not be very large. However, at the poles here, the air is cold and dry, and a little extra heat and a little extra water vapor could rise temperatures by a large extent. So for example, in October 2020, in the Arctic, the average temperatures for the month of October was 12 degrees above the long-term average. And really, this is why also we observe a very much faster melting of the Arctic than previous models have predicted. And if global warming will cause more extreme weather patterns, such as hurricanes, this is very likely because warmer temperatures absorb more soil moisture. That means that there will be increases in the amount of water vapor that enters into the atmosphere with global warming. Water vapor stores energy, and with a warmer atmosphere, there will be more energy stored, which leads to more extreme weather events. And because of this, one of the primary concerns in estimating the impacts from climate change on agriculture is to estimate the potential changes in the variability and the intensity of extreme events that accompany global climate change. So, what are extreme events? How can we define this? Here you see the vertical blue lines. Sorry. The vertical blue lines here are the average summer temperature for each year in Europe since 1980-64. And these range from about 15 degrees to a little less than 20 degrees since 1964. In 2003, Europe observed the hottest summer in 140 years, which is far outside the normal and observed range. This heat wave caused more than 70,000 excess deaths. And you can see from this example, one characteristic that such an event is extreme due to its very specific nature. It is outside of the range that has previously been seen. So these extreme weather events are by definition rare, and there are only very few observations of these because they are extreme. And if they would be normal, well, they would not be extreme. And this characteristic of a rare event complicates their prediction and their forecasting. So at this point, we must make a clear distinction between climate and weather. Weather is the state of the atmosphere at some place in time, usually expressed in terms of temperature, air pressure, humidity, wind speed, precipitation, or cloudiness. This is what you see in the weather forecast after the news, for example. So it is meteorologists who study weather and who do weather predictions that tend to be local and relate from today to the immediate future, maybe for days or for weeks. Climate, on the other hand, is defined in terms of the average weather or the mean weather over a long period, usually 30 years, according to the World Meteorological Organization. So it's temperature or precipitation over 30 years, long time spans or more or longer. It's climate scientists study these averages and trends of weather that have occurred over many decades, maybe centuries or even millennia. So in the figure here, you see the increase in mean temperatures with a shift to the right to a new climate with different weather patterns. And with this shift, in the shifting increase in mean temperatures, we observe a more hot weather, but also more record hot weather. And also it can stretch the curve further. So an increase in mean temperature makes it likely also to to observe more more extreme weather events. So what are these extreme weather events? They are usually defined in terms of in a comparison to a historical weather of weather record in a particular region. And these weather events are considered extreme if they're unlike from weather events that happened before, such as with the example of the European heat wave that I showed on 2 slides earlier. It is usually quantified using percentiles, for example, above the 95th percentile, or in absolute extreme values above a threshold. And these thresholds are arbitrary and it can depend on many patterns. For example, a precipitation threshold where the lack of precipitation is extreme also depends on the water holding capacity of the soils in a particular region. So they depend on local conditions, also on the plants that are planted and on microclimates. There are some secondary events of extreme weather events, such as floods, landslides, and wildfires, but I will largely ignore these here. Examples for temperature events associated with climate change includes that more warm days and warm nights, fewer cold days and cold nights. Can include a higher intensity and longer duration of heat waves, for example, through more hot days and more hot nights. It can be a higher drought frequency and severity for some regions that respond to changes in rainfall variability. And warmer air, as I said, it raises evapotranspiration. It can therefore exacerbate drought occurrence. Weather extremes have always, weather can be extreme by nature, and weather extremes always had a great impact on humans and ecosystems. But with climate change, it is very likely that the frequency and intensity of weather extremes will increase. Here, precipitation extremes. As I said, more water vapor in the atmosphere because of higher temperatures imply that more energy is stored in the atmosphere. And there's a direct relation between water vapor and a magnitude of extreme precipitation. And for this reason, the frequency of extreme precipitation events will likely increase in many areas on the world, and we already observed this in many areas. Regions with lower precipitation may still see an increase in heavy rainfall events because of a change in the variability of precipitation over time. We do, however, know, or scientists know a little less about the impact of climate change on precipitation because there are very strong regional and sub-regional trends that are very specific to microclimatic conditions, soil conditions, and the vegetation in a particular region. These questions are still from my side. More questions here.
Yes, we have some.
Very good.
Really great. So I see the first question from Ms. Mishenko. How do you think climate change has affected Antarctica, and how can it affect the world at large?
Okay, this is a very broad question. Thank you. Rising temperatures cause the ice to melt, and we can see this in the Arctic as well as in the Antarctic. There has been, I think, a record-sized iceberg, ice shield has been broken off the Antarctica. I think it's called the Larsen Ice Shelf, has been monitored with satellite imagery. This has large effects also on the animals that live along the oceans on Antarctica, which is really a biodiversity hotspot. The poles, as I have said, they warm much faster than latitudes close to the equator because they are dry and cool. So the effects are really massive on our ice shields, which will in the long term also cause a lot of increase in average sea levels. Yeah, it's also that as we see, as the ice is melting, there is more dark sea surface exposed. Sea surface has a much higher, stores much more energy than ice. Ice has a much higher albedo, so it reflects the energy back into space, into the atmosphere. So there is also a positive feedback cycle through the melting of the ice, through the increasing absorption of energy in the darker colors of the sea.
Okay, thank you very much. We have some more questions. One probably the question from Mr. Dovhoshia. He writes that it might be the question of topic, but still, how do you feel about the complete transition to the use of alternative energy sources? Is it possible?
Okay, this is a great question, and it's probably the key question for the future of humanity, at least in the long term. So I must say I'm an agricultural economist and geographer, and not a climate scientist, and nor an energy specialist. I think I do read some scientific papers about this topic and transition to alternative energies, and I do read a lot of popular science articles about this. So technically, it's possible. There are a lot of technologies available. It all depends on the right incentives from policy. So for example, if the carbon price would set correct incentives, then industry would probably transition very quickly to alternative energy sources to a large extent. Now, for example, in Germany, the policy is that we need to be at net zero emissions by 2024, and this is only 15 years away. No, it's 25 years away, 24 years away. But that means that we have to transition to alternative energy sources within basically the next 10 years. And if policy incentives are right, many scientists say it is possible. It is a major change, but it is possible because the technology is available. It will be, of course, a massive interruption to the way of life that we have experienced it in the past.
Great. So here we have a hope. And we have some more questions. So the next one may be more bound to the chemistry, but still very interesting, especially for me. Molecular mass of CO2 is heavier compared to an air. Does it really uprise to a stratosphere, atmosphere, and make a negative effect on global warming? Probably another green gases influence to a high extent compared to CO2.
Well, I'm not a chemist either. It is not my field. It is a fact that CO2 concentrations are rising in the atmosphere, and all serious climate scientists agree that these rising concentrations can only be due to human activities, mainly the burning of fossil fuels. And therefore we see this rise. Because CO2 is a greenhouse gas in the atmosphere, just as methane and water vapor and ozone. And with the rising concentration of these greenhouse gases, we see the warming of the atmosphere, which is again a law of physics. So I don't think there is any doubt about this in any serious literature. I'm not sure what the other green gases influence, what is meant by that. So CO2 is not, of course, not the only greenhouse gas, but it's the one that has been rising by far the fastest, and therefore it has a massive influence. Of course, it has only say 400 parts per million, so it is a very tiny component of the atmosphere. Most is water vapor, but the rise in this component has been causing much of the global warming, followed by methane, nitrous oxide, and the other trace gases that I had on the slide before.
Thank you Much. Maybe we will use another one question, and the rest will come to the next questions session. So the next one question is from Mr. Wojtenko. The field of my scientific research is the quality and quantity of irrigation water for agriculture production. My own data and the data of my colleagues indicate that the most severe water shortage will be the limiting factor for agriculture production in Ukraine. What are your forecasts in this area?
So I note this down. Sorry that here's a word opening. I note this down. This is an extremely important point, I think, but I would like to postpone this question to later when we discuss about agriculture in more detail, including irrigation and how irrigation can serve as an adaptation strategy, and how water shortages, as you say, will be a limiting factor for future agriculture production in Ukraine, not only in Ukraine, but also in Germany, for example. And I have a slide on this as well a little bit later. So thank you for this question. I postponed it to later. I have noted it down.
Okay, thank you. Great. So we have some more questions, but as I have told you, probably we will use them for the next session. So just for continue our presentation. So please, colleagues, write your next questions. We will come to them. But I'm pretty sure that we have another very interesting information in our presentation. So just let us hear about this.
Okay, so what I actually have planned now, but we don't have to do that, is a short break, because what my online teaching experience tells me, people want to stretch legs and grab a coffee, but it's up to you. It's an option. So Maria, please give me a hint. Should we have a short break to stretch legs and have a cigarette for those who smoke, or should we just continue?
So maybe I will be the bad the bad one, the bad policy, but still I would suppose that we will not obligatory have to organize this break, because we have to use the possibility of getting more information from you, and we are a little bit limited in our time.
Then
am I right,
continue.
Mr. Labenko? You have some other comments on this?
Maria, we are limited just maybe 1.5 hours. So right now maybe we have half an hour.
Okay, then let's continue. I will speed up then.
Thank you.
Okay, thank you very much. We go deeper towards the core of the topic that we do research about, and the seminar, how climate change and weather extremes impact crop yields. To start off, here's recent evidence of the effect of a 1 degree Celsius increase in global average temperatures on yields for 4 major crops. And you see estimates of global crop yield changes in response to this increase that have been simulated with crop growth models. The circles indicate the mean estimates, and the bars are the error bars for a 95% confidence interval. And here, these bars are the mean estimate. The figure shows that yield reductions are likely for all these crops, but that they may be particularly acute for maize and wheat. This figure also shows that there's a large uncertainty to all these estimates. So the message is also, we do not know a lot how climate change will actually impact crop yields. So large yield reductions are expected, but there's also high uncertainty. It could be very bad, or it could only just be bad, basically. So if we go to a 3-degree warming world, which we would probably attain by 2060 on current emissions trajectories, maybe 2070, we can see that agriculture will be adversely affected in many parts of the region, but there's a tendency that the global north will benefit from higher average temperatures due to longer growing periods, the melting of the permafrost soils, for example, in the boreal region. But the scientists are also pretty sure that the global south, which already experiences very negative effects, will experience much more negative effects in the future. And there's a big caveat here that it doesn't include, it's the increase in average temperatures. It doesn't include the effect of extreme events, because the models cannot accurately predict the frequency and intensity of these extreme events in the future, just for the fact that these are extreme. So if we go back to what we have, so this is the yield reductions that we observed due to drought loss, which these are projected changes in the risk of a yield reduction in the future, on the vertical axis versus the historical risk. And each dot represents a simulated risk as a summary of 11 different models with different climate models. And the gray arrow lines are the corresponding uncertainties arising from these models. We see here that the risk of yield reduction will likely increase for all crops, for wheat and for maize in particular, as we have already seen in the previous slide for the past. And these are only the effects of drought, so extreme events. The magnitude depends on the crop type and the severity of the drought. So more severe droughts will have a larger impact than more moderate droughts. And there are, what is not shown here, but these drought-induced losses may be particularly severe in some of the major global bread baskets. In the Eurasian steppes, for example, where Ukraine is part of it, in Australia, a major global wheat producer, in Latin America, mainly Argentina and Brazil, which already suffer from an increasing frequency and intensity of droughts, as well as in the northern US, where water also is really one key bottleneck, and droughts already compromise yields in many of the years that are planted. So, but how can temperatures affect yields? Generally, crops have an optimal temperature for their highest performance in terms of yields. Here shown with the dot here on the top. And beyond this temperature, yields are prone to rapidly decline due to heat stress imposed by higher evapotranspiration and evaporation. This is stylized here with this temperature yield curve. At a certain temperature, crops attain their yield maximum with an attached annual variability. If mean temperatures increase beyond the optimum growing temperatures, and assuming an identical yield variability, then this is shown here, then this can result in a much higher yield variability, even if the interannual temperature variability remains identical. This temperature variability is still the same. So in the absence of adaptation measures towards, for example, breeding drought-tolerant crops or heat-tolerant crops, we observe a much higher variability in crop yields, which is, of course, not only a concern for food security of humanity, which is also a major concern for individual farmers who have to deal with a possibly higher variability in crop yields, but also in their returns in the future. Here, this concept is exemplified with empirical data for the example of maize and 5 of the main maize-producing regions, including Ukraine here. The figure captures top producing regions, so the 6 largest maize producers on Earth and 6 largest exporting countries. And the curves are so-called density functions of yield for present-day climate conditions as the average from here, 1999 to 2008, the black curve, current climate. So at present, yield variability is fairly low. As we can see here with the spread of the black curve is fairly small. This is the yield variability at present. With a temperature rise of 2 degrees Celsius, this is the blue curve, and 4 degrees Celsius, which is the red curve, will cause lower average yields, a lower height of the curve, but also a much larger variability. It's a larger spread of the curve along the x-axis. And this is the same pattern in all of the major bread baskets that are here. Note these are the most important maize producing countries. So it is also much more likely that yield shortfalls or yield shocks will occur at the same time in several bread baskets. We have already observed what this can cause. It can cause major increases in food prices. And this is a concern, particularly for poorer consumers who have to spend a much larger share of their household budget on purchasing food items. And these are staple foods. So, okay. So now I zoom in a little bit to Germany, only 2 slides here. And so here you see the same warming stripes that you have seen before for global average temperatures. For Germany, of course, the variability is much larger because the territory is much smaller. So Germany witnessed 3 consecutive drought years from 2018 to 2020, which caused extremely low values of soil moisture. The map here shows a modeled soil moisture. This decrease in soil moisture caused large damages to crop yields and also caused very dramatic effects on forests, particularly on forests with on tree species with shallow roots that cannot reach the soil moisture that is now very deep down in the soil. And the replenishment of this soil moisture may take many years. So this is really a big worry for the future of German agriculture. Is soil moisture, and there's a lot of talk, can we increase irrigation capacities? Who will pay for the water? How much will the water cost? In which areas do we have water to respond to these extreme challenges caused by droughts that we already experience? So now I will zoom in further to Ukraine, here the Eurasian steppe belt, with some empirical evidence. You know that we have here, this region is characterized by large tract of Chernozem or black soil with a very high content of humus and minerals. It's a very fertile soil with high soil moisture storage capacity, which can be really an asset in the face of climate change. You also see a lot of Castanosem soils that are a little brighter than the Chernozems in these steppe regions, and also Phaeozems that are dark soils mainly found in the more humid and subhumid grass steppes. This area is characterized by intensive agricultural use, in particular wheat, but increasingly also soybean production, and can also serve as pastures for cattle. These similar soil conditions are found in Uruguay, Argentina, also in the northeast of China, and in the Great Plains of the US. The Eurasian soil belt is a major producer of wheat, about more than 20% of the total harvested area and production of global wheat, and also a major exporter of wheat to many of the surrounding regions. However, the region is also a hotspot of global climate change because the landmass has already warmed a lot faster than in other world regions because of the continental characteristics of this landmass. So we are, and you in Ukraine and the Eurasian soil belt in general is really a hotspot of global climate change. Okay, so now we zoom in to Ukraine, the last block of the seminar. where we want to discuss the impact, the potential impact of climate change on Ukrainian agriculture. Some more detailed insights also from our ongoing research. Here again, the warming stripes of Ukraine. Again, of course, the patterns are much more heterogeneous compared to the global picture because the territory is smaller, but you clearly see the rapid warming already, in particular over the last 10 to 20 years. That has also been observed globally, that has also been observed in Germany. Now to look at the past, here we quantified the coefficient of variation at the national level using detrended yield data from FAO. For Ukraine, we used the detrended provincial yield data. You can see that Ukraine has a very high variability in wheat yields for the period 2010 to 2017, expressed as the coefficient of variation. So basically the standard deviation divided by the mean expressed in percent terms. So this yield variability is similarly high in Kazakhstan, as well as in Australia, other regions that are partly characterized by semi-arid climate conditions and by, at least in the case of Kazakhstan, by a continental climate. Also, Russia has a pretty high yield variability, whereas Russia here, up here. Yeah. So yields from year to year, they fluctuate a lot because of different weather conditions. Now, Ukraine has about 6.6 million hectares of wheat area planted. Germany, for comparison, has 3 million hectares. 97% of the wheat of Ukraine is winter wheat. So it's planted in the period of autumn, where it enters the first vegetative phase, and then it has a winter dormancy, again enters into a vegetative phase in early spring, then reproduces, the so-called reproductive phase, and the grain filling phase until harvest sometime around August. As I said, the climate in Ukraine is highly continental with very hot summers and cold winters, and in each of these growing stages of the wheat plants, weather extremes can have a very different impact for plant growth. So for example, cold hardiness, Winterhärte, during the winter dormancy, where the wheat plants need a protective snow cover to protect the plants from very, very low temperatures, because the roots can only continue to grow as long as the soil is not frozen. So, and in the following, I show how we estimated the effects of climate and weather on wheat yields, taking into account these different development stages of winter wheat in Ukraine. So just to mention again, extreme weather events, which are very likely become more frequent in Ukraine, can have an effect in the different plant stages. So for example, a lack of snow in winter doesn't provide the protective cover to protect the plants from a frozen soil. There can be late frost which protects the revegetating plants early in the season. There can be an extremely wet early season. There can be drought stress in summer. There can be water stress. There can be stress to lodging so that the wheat plants fall over before harvest because of excessive rain, for example. So there are various weather extremes that can affect wheat growth over the time of development of the plants. So in our research, we use daily data to capture extreme temperatures and precipitation events. Why daily data? Because to capture the spikes in precipitation and temperatures that characterize the extreme nature of such events, for example, extreme heat, extreme frost, extreme rainfall, extreme little rainfall. We use globally and freely available data for climate and precipitation that are available in near real time and to anybody on Earth. We also use soil moisture data and vegetation indices in these models. And And one bottleneck in such research, unfortunately, is that it's often difficult to obtain accurate time series of the crop yields in order to associate crop yields with weather and climate variables. So we use provincial level yields, as I will explain later. So the global climate and precipitation data comes from daily temperature and precipitation measurements from 190 weather stations spread over Ukraine. We analyzed for these models the steppe region and the Northwest separately, and we used for the analysis the period for 1985 to 2018. So the steppe region is, as you know, semi-arid, has large tracts of black soil, and the Northwest is more humid with higher average temperature, with higher average precipitation, but lower average yearly temperatures. On the right here, you see the increase, extreme heat days using a threshold of 34.4 degrees in this case, based on literature of other agronomists who have done similar research. 34.4 degrees temperature in June or July, and at this temperature level, scientists have shown that the wheat plants experience substantial wheat reductions. So we use a random forest model, which is a machine learning algorithm that is based on many decision trees. It combines many decision trees in order to associate climate and weather variables with the yield data. As yields, we use provincial level yields of winter wheat for the period of 1985 to 2018. And as covariates, we use the climate mean, such as temperature and precipitation, but also several weather extremes in order to find out their effect on wheat yields over time, and which variables are the most important variables that shape wheat yields in Ukraine. We estimate this for the growing season of wheat plants and also specific to the development stages of wheat over the course of time. The results that are here shown on the right show that, I hope you can see that, show that the models that are specific to the growing stages of the wheat plants have a higher predictive accuracy than the models that are for the entire season. So this corroborates that the individual plant development stages are really very important in any statistical assessment of the relationships between wheat yields and weather events, including extreme events. So the models calibrated for the plant growth stages better explain the yield variations, and weather extremes are also add additional explanatory power according to the climate means when we use here all variables on the left. Here we only use the weather extremes, and they can already explain, by the way, almost half of the variation in wheat yields. Of course, a lot of the unexplained variation is simply management of farms. Yeah, how much inputs do farmers apply, what kind of plowing technique and so on farmers use. But more than half of the variation in yields can be explained by climate and weather. Yeah, this is a slightly complicated plot. I don't want to spend a lot of time on it. So it basically explains that we can deduce the importance of particular variables as well as nonlinear responsive of individual variables along the data range. So the legend here on the top, it signals that variables with brighter colors towards yellow have a higher predictive power, are more important for wheat yields. So the reproductive phase, as we see from the graph, seems more important than the other phases. In terms, it has a higher variable importance. It tends to have a higher variable importance. We can also look at selected plots here. Here, selected variable plots. So, for example, here we see that when we have more than about 2 heat degree days, that is temperature exceeding the heat threshold of 34.4 degrees for at least 3 consecutive days, then we observe a large negative impact on wheat yields of heat events. Second, when we observe more tropical nights, then more than about 2-3 tropical nights, then the effect on wheat yields will be increasingly negative and then flattening out at many tropical nights. Here we have, of course, very few observations. So the essence is we can assess the impact of individual variables on yields, and we can see at what levels of the intensity and severity of extreme events we observe particularly strong yield increases. So the key results of such research is that models need to be specific to the plant growth stages because they can explain much more of the yield variability. Climate and weather explains more than 50% of the year-to-year yield variation. And it is mainly water stress that limits yields during the reproductive and grain filling phase in the steppes. And higher heavy summer precipitation reduces yields in the northwest. So the effects are really specific to particular locations. Weather extremes, in particular heat and drought and frost, have in general very substantial impacts of yields in Ukraine, and these need to be the focus of future research, because if we look at what is expected for the future of Ukraine, these are now a little bit older projections, but now with the 6th assessment report of the IPCC, the International Governmental Panel on Global Climate Change, with the new report, more updated figures will come out, but we see a substantial increase on average temperature until 2070, particularly in the steppe areas, particularly towards the northeast of Ukraine. And we see also that potentially there will be vegetation increase more to the northwest and a little increase in the southwest. What we cannot predict, or what climate scientists cannot predict, however, is how extreme events will develop in the future, and also the predictions on precipitation have a large uncertainties associated. So overall, the impacts of weather extremes on agriculture are fundamental. We will observe more frequent, longer, and more severe droughts and floods, including in Ukraine. Soil degradation will be a continuing problem because of decreasing soil moisture, increasing erosion and salinization, and these need to be tackled in adaptation pathways. There will be a higher prevalence of diseases in crops and livestock in the future with rising average temperatures and more extreme events, because both plants and animals may become more susceptible because of the stress imposed by extreme weathers. The distribution and competitiveness of wheats may increase. We are not really sure about this, but and also the price volatility for outputs and inputs may increase because of the rising volatility of production in the future. As I said, there's a large uncertainty, however, in predicting the impacts of these extreme events on agriculture. So I suggest we spare the questions to the end. And now I come towards the end of this seminar, and then I hope we can have discussion as long as you wish on open issues. So the large block, adaptation options and future research priorities. You are at a university, so you have been very brave and long waited for this. So here's what I think. There are probably more, and some may be more important, others less important. So to ensure successful climate change adaptation, there are several changes that are critical, as I think, for the agricultural sector. So on the economic side, economic measures, it is changing managing practices that will be important to adapt to rising temperatures and more extreme events. For example, adjusting sowing time, adjusting the cultivars that are planted, adjusting the species that are planted to changing temperature conditions. And we already observed this empirically. Farmers sow later, they harvest earlier because of the average rise in temperatures. The switch to other crops is another important added strategy that is already observed. For example, to crops that are more water efficient, for example, from cereals to legumes, because water becomes scarcer and water becomes more precious because it becomes scarcer, and possibly in the future water will also become more pricey. Crop breeding towards producing crops that can resist higher temperatures, that can better resist heat or drought, will be a very important strategy for the government to finance and support, but also for researchers, including to facilitate the access of farmers to these crops, so to promote these crops among farmers. This will include possibly the development of new crop types, crops that are also maybe more salt resistant and better adapted to higher salt contents, for example, in irrigated areas. Drought resist, irrigation and higher water use efficiency, there has been a question before on this, will be really crucial to better adapt to future climatic conditions, including in Ukraine and particularly in the steppe region of Ukraine. This also includes that the efficiency of water and nutrient consumption of crops, so the water used per kilogram of output or the nutrient inputs that are needed per kilogram of output, will be important. This is, for example, drip irrigation that have a more precise application of water to the crops, or reduced tillage operations that better support to hold more soil moisture in the soil. Seeding at lower density is already happening in Ukraine, as we have heard from One Agro Holding. So they seed, for example, maize in much lower densities than they did before, so that the plants have less competition for resources. However, of course, at the cost of lower yields, lower output per unit area. What is, I think, an overlooked option, what I really would like to see more research about is these tree shelter belts that have been, I think, initially established across the Soviet Union by the evil Stalin, where these tree shelter belts, they around larger fields, they improve microclimatic conditions, they decrease air temperatures in summer through evaporative cooling, they reduce the effect of heat islands, improve soil conditions, store carbon in vegetation and soil, and reduce wind speed and therefore soil erosion. So I think these, they cost they have cost for management establishment, but I think in the medium term, they provide a lot of benefits, both for farmers, but also for society. There are also several risk management options that will be increasingly important. We do a lot of work on index insurances and how these can be established or produced with a low basis risk. Diversification of crops is of farming strategies towards a higher crop diversity and more diverse income sources is an important risk management strategy by farmer, but also the establishment of early warning systems for extreme weather events, extreme heat, extreme droughts will be important and should be a priority of the government and facilitated by research that underpins these systems. And there are other options for adaptation that farmers take. They try to accumulate more resources, more land. So they spread the risk about more land. So this also involves a more competition about land resources, of course. Many people exit agriculture because of problems imposed by climate change, including in Germany. And people start to emigrate from rural to urban areas because of the pressure posed by climatic changes. Now I have talked a lot. And now I would like, I see some Slido questions. Thank you very much. Okay, so maybe some questions to this, and then I have one more slide on research priorities.
Thank you very much. I see we have really a lot of questions. It's great that our participants also used Slido for posting some questions. Maybe just one step back, would you like to add something on your forecast to the limiting factor water for agriculture production in Ukraine, or it might be already enough? What was said? And maybe in general, one question from Ms. Fineva: why do you think the climate in Europe has changed so much in recent years? Maybe one small comment on that.
Yeah, on the climate in Europe, the climate has changed everywhere, including in Europe. As I said, the 1 degree global average temperature increase implies a 1.5 degree increase on the land masses. And this has, as we observe, increasingly massive implications on weather, including we have more extreme events such as the drought in Germany that brings really many farmers to the brink of survival in 3 consecutive years. And Germany is not known to be a desert area, but in many regions we have precipitation below 250 millimeters per year, including in some of the best areas in terms of agriculture in Germany, in the black soil areas. So this climate change is really affecting everybody, and most countries are negatively affected, and the effects become more negative the further south one moves, tends to move, and the more continental the climatic conditions are.
Thank you very much. One more question from Ms. Mishenko. She writes that it might not be the question on the topic, but still it is, as I can see. What is your opinion on the increase of agriculture, including crop and livestock, of pests that were pests that were not previously in that place of residence? And the question is, how can humanity deal with this?
Pests for crops.
Pests for crops and livestock.
Yeah. It as the framework, the conditions change, the climatic conditions change, there will be new challenges, including from pests and diseases, not only for animals and plants, but also for humans, as we have badly observed now. Research is needed to adapt agricultural production to these new challenges from emerging pests. I think it is not all negative. I think research has also become much better in producing plants, in cultivating plants, and farmers have been better in adapting to diverse conditions. So also the technologies they advance in order to cope with such challenges, such as from growing pressure from different pests and diseases.
Mm-hmm. Okay, thank you very much. Next question about modern methods of predicting and preventing dangerous natural phenomena from Mr. or Ms. Stepanenko. What are the modern methods and methods for prediction and preventing dangerous natural phenomena? I suppose that there are a lot. So maybe you can just mention a couple of them.
I'm not an expert, so I assume this is on the dangerous extreme weather events, for example. It's a good question. The predictions of weather become better. But if you look at your weather forecast, you sometimes wonder why often the weather that has been predicted five days in advance does not appear to be true. So it's very difficult to predict weather for small areas because the climate system is a chaotic system. So small changes can have a large effect, and these small changes can often not be anticipated. However, climate scientists and meteorologists become better in, and the models that they use become better and much larger in doing this, such as weather predictions. So they tend to be able to predict weather better into the future. We see, by the way, in the corona pandemic, in the COVID-19 pandemic, that the weather predictions have become a lot worse. And this is simply because there are many less planes in the air who have always transmitted weather parameters from their flights to weather stations, and which have been used by these weather prediction models. So when we have more planes in the air, also these models will again become better. So there are tools and models to better anticipate also extreme weather events. So scientists are pretty good in predicting storms a day or two in advance, sometimes even longer. And these tools, they become better over time. But in general, an extreme event is still extreme. So often it is for statistical reasons, it's difficult to sort of anticipate these peaks in a time series.
Okay, thank you very much. One question from Mr. Pravidny. How harmful is the impact of the ozone hole on our planet, and how can this layer be restored as it harms the climate and agriculture? So maybe a couple of words about ozone hole.
So I'm on slippery ground here because it's also not my field of expertise. So we had big problems with the ozone layer in the 70s and 80s. Actually, through the Montreal Protocol, I can't remember the year exactly when it was established, this is the only global corporation where the global community has shown that it can do something together to tackle an environmental problem. So the ozone layer is still there, of course, yeah, the ozone hole, but it has dramatically shrank over time because the global community worked together and limited the use of fluorocarbon, I don't know, FCKWs in Germany is the abbreviation, mainly used in refrigerators. But this success is because the costs were very small and the benefits were very large. So it was easy to work together. In climate change, this is different because the costs to mitigate emissions sound very large, and the benefits will be distributed globally, so nobody wants to do the first steps. So yes, the ozone layer is still a problem, but it has reduced. But you better still use sun cream when you go out to protect your skin from skin cancer due to a higher ozone, due to the lack of ozone in the atmosphere.
Okay, thank you. The next question also from Mr. Pravedny, more bound to agriculture. What would you recommend growing in the south, which is now suffering from climate change?
Yes, another good question. So I think there are many agronomists, maybe even in the audience, who know this better than I do. So I am not an expert in farming in Ukraine. I think you need to think of crops that are more resistant to low precipitation, maybe even droughts, and that are more resistant to extreme weather events, which will be particularly acute in the south of Ukraine. So these are crops that don't use a lot of water. So probably not, for example, maize, which uses a lot of water, but rather cereals that are more water intensive. And this may go to some cereals that are planted now in conditions that are drier as it is now in Ukraine, such in parts of Africa, where they plant cereals like millet, a very healthy food. Maybe other cereal plants such as teff are more apt in, say, 10, 20, 30 years from now than the current used wheat varieties. But they will also progress in plant breeding, also in terms of wheat. So probably wheat and the other main cereals will be important, continue to be important crops in Ukraine. But I'm not an expert, really.
Okay, thank you very much for your opinion. Next question from Mr. or Ms. Bogdanets. Are there examples of positive effect of current climate change on the environment and or agriculture, or do you think it's estimated as total negative?
Yes, it's a good question. I don't want to be too negative here. I'm actually a positive person, I think, but there are also positive effects. So, for example, you have more solar radiation, you have more heat, which increases plant growth. Also, the CO2 content in the air, the higher CO2 content increases plant growth, particularly of C4 plants such as corn or maize, which grow faster. There are some regions on Earth, but these are actually only in the boreal region, really, that also benefit from climate change because of longer growing periods, because of the melting of the permafrost soils, which opens up new areas. So it's not only negative, but it definitely needs adaptation to the new conditions.
Okay, thank you. Next question from Ms. Proň. What do you think Ukraine can play in addressing global warming?
Yeah.
So some advices for Ukraine.
Yeah, so every country has to do something to mitigate emissions. But I think Ukraine has other problems at the moment, and while Ukraine has to show that it makes efforts to mitigate emissions, the share of Ukraine in global emissions is really very small. Of course, every country has to reduce its share, or not its share, its absolute amount. But I think the effect of Ukraine on global emissions are fairly small. However, there are future energy sources that also provide other co-benefits besides mitigate emissions. Better air quality, mainly through renewable energy, because you burn less coal, less oil, less gas. So better, less air pollution, and also a more sort of, say, nicer landscapes. And there are a lot of co-benefits in reducing the emissions of fossil fuels. But Ukraine can also do a lot more in its agricultural sector to address mitigating emissions. And this is through sequestering carbon in soils and through sequestering carbon in the atmosphere, in the vegetation, sorry.
Okay, thank you very much. One more question about your opinion from Ms. Olejnikova. In the 1940s and 60s, there was a global cooling. Yeah. At the same time, greenhouse gas emissions are a result of human activities increased. Isn't this proof that the concentration of CO2 does not affect the temperature?
Yeah. Okay, thank you. No, but this is not a proof, simply because it's not higher CO2, warmer weather. It's not a one-to-one relation in every year. It is, again, climate is the long-term average, at least 30 years. But if we look at this, or climate scientists look at this in terms of centuries, millennia, millions of years even. And then this relationship, which is a physical fact, can be established, and it is very strong. Now, of course, there will also be in the future, there will be cooler years. Average temperatures will go down. We had here in Germany a very cold April, the coldest April since 1880 or something like that, or 1920. But this is weather, and we shouldn't confuse weather with climate. And in the long term, the effect is clear. We will observe weather variations in the future, but the trends are clear, and the physical facts that cause these trends are also clear.
Okay, thank you. Some more questions, if you allow. So from Ms. Stachiev, in Ukraine, abnormal weather phenomena as hail, squalls, tornadoes. Okay, tornadoes in Ukraine, something new for me. In area of which they were atypical, which previously occurred once every 50 or 100 years, were increasingly observed. Why this happens and how we can avoid this. So maybe just a small addition to what you have already told us.
Yeah, thank you. Yeah, this is correct. It's the same observations we have in Germany. This is related to higher temperatures, which store more water vapor in the atmosphere, as I said before, which implies more energy in the atmosphere, and this energy we experience as more extreme weather events, and this will probably increase in the future. At least this is what all scientists expect. So you can only avoid this through reducing emissions. The global community needs to avoid this through reducing emissions, and then the effect will be dampened. Of course, we will still observe more climate change if we are at zero emissions, because the system is static and CO2 has a long time that it rests in the atmosphere. So you need to prepare for it. You need to be ready for observing more extreme weather. And in the long term, the global community needs to reduce emissions in order to make these effects not occur even more than predicted in the trend.
Thank you very much. Next question is from Mr. Zas. I suppose an interesting one about policy. Now, statistically proved is an increase in temperature of about 2 degrees over recent 5 decades, more or less, same as predicted for the future, accompanied with nearly no climate policies, as well as increases of harvest. Would you confirm that agriculture management would have sufficient resources to buffer potentially negative impacts by climate change? So now need for specific policy approaches with regard to adaptation of agriculture.
Yeah, this is a good observation. So we have climate change, and at the same time yields in most areas, not all, by the way, some areas just lower yields, but yields on average have increased, including in Ukraine, where yields have actually increased quite substantially. Yield increases are mainly due to better management, more inputs, better plant material. And climate change has reduce the yield increases. This is what the statistical results suggest us. So there would have been more increases in the absence of observed climate change. So globally, there has recently been a much cited and talked about study that said that so global productivity increases, yield increases would have been substantially higher without climate change than with it already. But then you have to note that we have only seen, if you recall my slide towards the beginning, we have only seen very little, and what we expect is a lot more. So we can really expect that in the future, there's a much larger need for adaptation to climate change, simply because the effects will become much stronger. And this is what we have observed in the last 5 years, for example, where one weather record was beating the other. So in the medium long run, we need climate policies, we need more adaptation and research into adaptation of agriculture, because the effects will very likely to become more stronger. And even if the scientists are incorrect that these effects will not be stronger, it is always better to be prepared than to ignore this, and then it comes as a surprise.
Yeah, thank you very much. Thank you for your opinion. And the last question by now in our chat from Ms. Volashuk: how will the issue of climate change affect the irrigation in the world? And will it be possible to solve the problem of the water shortage in the field of agriculture?
Mm-hmm. There has been a question before. Thank you for this question. There has been a question before on the importance of the quality and quantity of irrigation for agricultural production. Yes, irrigation is one adaptation strategy. It will be important. However, it is expensive for farmers, expensive to establish, and water will become scarce, in particular if many farmers start to use irrigation water. We have groundwater resources are usually non-renewable. Precipitation may not increase a lot. So if we use a lot more water through crops, then there will be water scarcity in the future, which is possibly also the case in southeastern Ukraine, in the steppe areas where water will be short. So yes, it is an important adaptation strategy, but it will not work everywhere. It will be expensive, and the water usage has to be very carefully monitored, which is not so easy, as we see in many examples across the world where water has been used excessively in agriculture, causing water shortages.
Thank you very much. Thank you. And thank you very much, our participants, for your active participation in our questionnaire. I think that was really interesting. So maybe now we can come to the last question, as Mr. Müller has mentioned about the future research priorities, what should be also interesting for our scientific colleagues.
Yeah, thank you. We are running a little bit over time, not a problem for me, but maybe for you. So very quickly, I will provide these slides so you can read it with time later on. There are a lot of research priorities. So climate change is the most important mission for universities of the 21st century, as some very clever people said here. I think this is true. So if you work on climate change or intend to work on it, there will be plenty of work for you in all sorts of areas. So of course, it's to assess the impacts of future climatic conditions on agricultural production. There are many aspects towards this more broader research arena. Quantify the effects of weather extremes on crop and livestock productivity, including the effects during crop-specific development stages, as we have shown with our work in Ukraine, for example. Research to examine the effects of climate change on production intensity will be important, including on how input applications can maybe adapt or maintain yields at high levels, and also to examine the effectiveness and efficiency of available adaptation options. And I have mentioned many options on the slides before, will be an important research priority. With this, I'm here at the end. So I think it's very important that we have to sort of consider that climate change is real and has already substantial effects on agricultural production. The frequency, intensity of extreme weather will intensify. We will observe more extreme weather events and therefore higher crop yield variability in the future, but it remains challenging to predict and prepare for such extremes. Technological progress will be crucial to cushion some of these adverse effects, and adaptation options will become central for agriculture around the world, but also, and maybe even more so, in Ukraine. And this concerns policy, management, and research equally. And with this, I thank you very much for your attention. And I'm open for other questions here or privately by email.
We still have question whether it would be possible to get the answers on questions in Slido. There will be two of them. So sorry. Probably you could come back to them, please.
Yeah. I think they should load here. That's the... where are they? Yeah.
Exactly. Mm-hmm.
Yeah. Okay. So, yeah, I will answer the questions in Slido. I will write it down, yeah? In Slido, so you can see it there. Sorry for not answering these in the course. There were too few of them. I will answer them in Slido. You can look them up online.
Okay. Okay. Thank you very much. It's also one interesting format. So thank you very much once again for a very interesting lecture and answering so many questions. We are really very pleased of getting so many questions. It's great that the interesting questions are coming from our students, from our scientific staff, and that this topic is really very important and useful to be discussed for Ukraine and globally as well. So I see in chat also many thanks for our participants. Thank you very much, Mr. Müller. Thank you, our dear participants, for your patience also, because we have really took a lot of time, but as we can see, almost more than 50 of you are with us. It means that the information was useful and interesting for you. It's the most important thing for us from APD. So thank you very much, Mr. Lobenko, once again for helping in organizing this lecture. We are still preparing something interesting for you for the future, and we'll be really grateful for your assistance in the future in organizing such kind of lecture. Thank you very much, Mr. Müller. Hopefully in the future, that would be possible for us, despite of COVID-19, to be able to have more contact with you and get more interesting details from our planes for predicting better our climate changes in Ukraine, and also being able to make a journey that would be hopefully the best option for all of us.
Yes, I hope it was interesting for you and for the audience, and that it provided some food for thought and for future research activities at your university. It was a pleasure for me. Thank you.
Thank you very much. Thank you, dear colleagues. Thank you to our interpreter. Hopefully it was not too difficult to translate. Thank you for assisting us, and see you then later at all the other events organizing by APD. Hopefully that would be also useful and interesting for you. Thank you very much. Take care of you and see you soon.
Yes. Thank you very much. Bye-bye.
Thank you. Goodbye.